Good morning. I would like to begin by thanking the organization for accepting my paper in this workshop. The work I'm presenting today is titled The Nonlinear Dynamics of a Constrained Wave Energy Hyperbaric Converter. Wave energy is a growing interest among renewable energy sources. Therefore, the wave energy hyperbaric converter is not really a novelty. There are already two devices in prototype phase connected to the energy grid, one in Brazil and another one in Denmark. The main difference between these two is that the WaveStar device, here shown on the right side image, has to be installed in a big platform with 4 or more pillars. This allows it to be installed anywhere along the shore and maybe even offshore, and it allows it to adjust to the sea level, which changes with the tides. The one in the port of Pecém, Brazil, is supposed to be installed on the shore in an already existing seawall, making it much more simple, cheaper, and easier to install. Like any wave energy converter, this type of device requires a PTO system in order to convert the energy from the waves into usable electric energy. This functions by converting the oscillating movement of the floater and the arm to activate the hydraulic pump. This pump then gets water from a reservoir that's sitting at atmospheric pressure and pumps it at very high pressures into an hydropneumatic accumulator. Together with the hyperbaric chamber, these two components maintain a large amount of water at a very high pressure. Through a valve at the end of this system, the water is then expelled in the form of a jet into a Pelton turbine for conversion into electricity. This whole system guarantees that the irregular flow from the pump is converted into a continuous flow for better efficiency. The purpose of this paper was to study the dynamic behavior of a wave energy hyperbaric converter with and without mechanical constraints. In this way, it was decided that dual-S physics, together with Project Chrono, was the most suitable code for simulating this device. The smooth particle hydrodynamics method allows for a very precise interaction between fluid and floating structures, and the Project Chrono library allows to establish mechanical relations between various solid components. And also, it allows it to install mechanical constraints in order to simulate the PTO system with a very good precision. Despite dual-S physics having already a good reputation for simulating the interaction between fluid and complex floating structures, we considered necessary to validate the code for this type of interaction, this being a constrained floating structure. For that, we performed simulations with the same characteristics as the ones performed by WINT in 2020, in which they tested the WaveStar device both experimentally and numerically. We obtained good comparable results, proving that dual-S physics code is quite suitable for this type of numerical study. The first simulations were run without any PTO load on the system in order to depict the dynamic behavior of the device whilst it is completely free. There were only two mechanical relations as hinges between the floater and the arm and between the arm and the shore. However, for simulating the effect of a PTO system, a mechanical constraint was needed. This would be a torque applied in the hinge between the arm and the shore, here illustrated by the red arrow called M force, and it was supposed to simulate the force exerted by the pump on the arm. This torque can be easily calculated as a function of the pressure in the hydraulic pump, here shown on the right side image. K being the torque is equal to the pressure in the pump times the area of the piston times the distance between the pump and the hinge. However, the mechanical constraints available with Project Chrono were not the most suitable for this type of device. For now, Project Chrono only contemplates hinges that can be set either as a torsional spring or as a damper, which apply force dependent on position and speed respectively. And the PTO system we pretended to represent applies the torque I just explained, which is much more closer to a constant force, independent of speed and position, but always contrary to the direction of movement because the pressure in the pump is almost always constant. So we altered the CH-link force file from the source code of Project Chrono to achieve the torque we desired, and this was the small change we did. The result of this change was simply that there was an always constant torque applied contrary to the arm's movement of value k. Here shown as whether the velocity is positive or negative, M force is always equal to k times the modulator. In order to have a simulation flume in a 1:1 scale, closer to a real scenario, we searched for what would be a suitable location in Portugal for the installation of this device. After consulting wave distribution maps of the Portuguese coast, we decided that the port of Sines had the infrastructure suitable for this type of device, and by consulting nautical charts, we were able to get a close to real geometry of the wave flume. This was the final flume geometry we settled. We settled on a 160 meter long flume because we considered it was long enough to accommodate several wave periods, but not so long that it would cause very long simulation times. Initially, this was the geometry on the lower right side. This was the geometry used for the device. Very simplistic, but based on the real dimensions of the device already functioning in Brazil. With the geometry ready and simulation parameters defined, we started to run simulations without a PTO load, in order to establish the dynamic response of the device to different sea conditions. The main parameter we aimed to study in these first simulations was the response amplitude operator. This is easily calculated by dividing the floater range of motion, here shown by the red arrow as 1.01 meters, for example, and dividing this value by the wave height that is inputted into the code. After obtaining the response amplitude operator for each wave frequency, we plotted this graph for waves with a height of 1.5 meters. Here, we observe that for very high frequencies, which means small period waves that are very short in length, the device barely moves. As the frequency lowers, we come to a range of frequencies that are clearly better for energy extraction, between 0.14 and 0.18 Hz, that also correspond to the most frequent waves in the device's location. As the wave frequency lowers even more, we observe that between 0.1 and 0.12 Hz, the device also barely responds, but for lower frequencies than that, the amplitude of motion climbs a lot. This was at first glance quite unexpected, but after some thinking about this phenomenon, we realized this happened because of the wave shoaling near the shore. Wave shoaling being the effect by which surface waves entering shallower water decrease velocity and increase in wave height. This effect is quite more noticeable in longer period waves, which are longer waves in terms of length, and this results in this phenomenon we see here. These two are quite similar, but they are different graphs. On the left side, we plotted the amplitude of motion for each wave height, and on the right side, we find the response amplitude operator, which is basically the dimensionless version of the graph on the left. So on the left, we notice that as wave height increases, the amplitude also increases, which makes total perfect sense given that bigger waves tend to have more impact on the device. However, the frequency at which we obtain the highest and lowest values remain the same for different wave heights. This is confirmed by the graph on the right, in which you see that all four lines are almost all the same shape and values. But we observe that for higher frequencies, almost two sets of lines, red and green together and blue and black together. And this may be explained because of the different dp values that were used in order to reduce computation time. dp being the value of the distance between particles at the beginning of the simulation. After concluding the study of the device's behavior without PTO, we began the study of the PTO integration. Initially, we started to increase the value of K, this is the torque applied on the hinge, from 0 to a value when the device would barely move. As you can observe on this graph, as K increases, the range of motion of the device decreases drastically, until it barely even moves, as we observe on the pink line. However, it's very noticeable that the maximum height the device reaches isn't very affected, but the minimum height changes quite a lot. This is because when the device is moving up, the main force exerted on the device is the buoyancy force exerted by the water, and this is much stronger than the torque from the PTO. And so the net force doesn't change a lot with a stronger PTO. But on the contrary, with the device moving down, the main force is the weight of the floater, which isn't much stronger than the PTO torque, resulting in a slower descending speed. This led us to believe that maybe a PTO with a simple effect pump, this is a pump exerting force only in one direction when the device is moving up, might achieve better power results. However, we did not have the time yet to test this because it would also require further changes to the project kernel source code. The next step was to build a power curve like this one for each sea state, varying wave height and period. In this case, this power curve is for waves with 7-second period and 2-meter height, and marking the highest power achieved and the K value this corresponds to. For each sea state, we performed between 5 and 9 simulations to obtain the power curve, changing the value of K. We studied a total of 32 sea states, resulting in a total of 176 simulations with the PTO system. With all this information now available, we were able to build these maps in which we can determine the expected power and expected efficiency given that we know the wave height and frequency. We can observe that the best and worst frequencies for power extraction correspond to the same frequencies we saw on the simulations without the PTO system, and we also observe that the power increases with wave height, but the efficiency actually decreases. Most importantly, on the lower right graph, we know how the K value should evolve with the change in sea state. And as I explained previously, this value is directly related to the water pressure in the PTO system. So this graph shows us kind of how the pressure in the system should change with the changes in sea state. With all this lastly, we decided to study the influence of the seawall's characteristics in the dynamic behavior of the device. For that, we developed a new seawall geometry. This geometry is an attempt at simulating the effect of usual breakwaters built with rocks and cement blocks, which objective is to break the waves, dissipate the energy, and protect the structures above and beyond the seawall. In the video on the left, we observe that the water reaches both a higher and a lower height on the seawall than the video on the right. The blocks force the water to have more movement, filling more the spaces that don't yet have water, and this dissipates a lot of energy and reduces the reflected wave. This reduction of the reflection of waves is significantly noticeable when we look at these graphs. It's easy to notice a substantial difference in the amplitude of the device, but on the graph on the right, you observe that for some frequencies, the change of the seawall was actually beneficial, meaning the reflected wave actually worsened the device's performance in certain given sea states. This indicates that by altering the seawall shape and porosity, we can fine-tune this type of device's performance. The main conclusions we took from this paper was that initially dual-S physics is quite appropriate for this type of device. We learned what are the best and worst frequencies of waves for energy production and how we can control them. We learned how we should change the PTO system pressure and characteristics in order to achieve better power and efficiency results. And lastly, we learned the effect of the different characteristics of the seawall and how we can fine-tune these characteristics to get better power results. Thank you all.